Hey, Dr. B here, and let's talk about how we actually measure energy changes. As we've pointed out before, there are no energy thermometers, but there are temperature thermometers. Let's go over the actual processes of how energy might be measured by a chemist, and let's talk about how this might apply to some forensic applications and others. Well, let's take a liter of water. And let's think about how much energy is required to heat that stuff up. If we're going to change the temperature by 1 degree Celsius, we can measure how much it's known, how much energy that takes. And people use a lot of units. In this particular case, it's good to know them all. You see a lot of these used, you know? If you're dealing with tiny temperature changes or reading a scientific paper, you'll use joules. And that will require a lot of them. So it's a tiny measure of energy, 4,184 joules to change the temperature of a liter of water by 1 degree Celsius. An unfortunate term is the scientific calorie with little c. I'm going to try to avoid it when I can. It doesn't show up as often, and that's 1,000. The British thermal unit, BTUs, I've seen that for air conditioners and other things. We're dealing with larger capacity systems. It takes 4 BTUs to do that 1 degree temperature change for that liter of water. I really like nutritional calories because people are very familiar with it. That goes by the letter capital C, and you get a feel for it. You might know that there's like, 140 calories in a 12-ounce can of Coke, for example, but it only takes 1 nutritional calorie, and that's another reason why it's nice, right? It's tuned to exactly 1 nutritional calorie to take 1 liter of water and change it by 1 degree Celsius. If you're on an aircraft carrier, you're dealing with like the heat for your home, or you're getting your utility bill where there's very large amounts of energy involved. Now we're talking kWh, kilowatt hours, and it's way less than one. To make this a little bit more practical, let's imagine you are going to pound down an entire pint of Ben& Jerry's ice cream. Choose your flavor. You'll be dealing with over 4 million joules of energy that you're taking on board. Yikes. A million scientific calories, about 4,000 BTUs, about 1,000 nutritional calories. You can probably verify that, right? All that heavy cream and everything. And only about 1.16 kilowatt hours. So all these unit conversions are valid, and you should be familiar with how to interchange them. A lot of this energy change deals with water, and that's water has it's very hard to change the temperature of water. It requires 4.184 joules to change the temperature of 1 gram of water 1 degree Celsius. That might sound like a low number, but there are almost no substances on planet Earth that are higher than that. It has a very high specific heat. It requires a huge amount of energy to change it. So, what is specific heat? I think of it as sort of as the heatability of a substance. It's resistance to a temperature change. Note that it's not done by volume, it's done by mass. So, if you have a big iron frying pan, you find it's relatively hard to change the temperature of it. Well, it's also very heavy, so you have to take that into account. So the really high density substances almost give you misleading data. Anyhow, that's the amount of heat that's necessary to heat 1 gram of water by 1 degree Celsius. Fine. And it applies overall to the specific heat formula. Let's go over these terms. The heat involved will always be equal to the mass, right? 1 gram, there's your mass, times its specific heat. That's its difficulty, how difficult it might be to heat that substance. It's a really nice number to know about each substance. And, it's curious to look them up. Times that change in temperature, right? Joules per gram per degree Celsius. And here's some numbers. Liquid water is different from solid water, different from gaseous water. Ethanol is, not that easy to heat, but the metals surprisingly show up lower, and I think that oftentimes has to do with the fact that they are 2 or 3 or 7 times as dense as water. Okay, so let's apply this to a problem, right? Here's some beryllium, magnesium, calcium, strontium, and barium. Bemka cerbera. This is the group twos. There's their specific heats. And let's try to say you had an issue. You took a chunk of metal. It weighs 4.68 grams. You heat it up you give it a temperature change of 182 degrees. You find that it absorbed 256 joules of heat. What metal is it? It must be strontium. It looks like we're solving for C. So if Q equals mc delta T, C must equal Q over m delta T. There's your m, there's your delta T, there's your Q. Plug them in. It's strontium. Similarly, you should get them for the other two. If you're really concerned about this, I'd recommend you practice one of these. Actually do it and see if you can solve for those problems. Here's another problem. How many joules of heat would it need to make a cup of water? So it's tea time, right? And you want to make a cup of water. Well, you've got a unit of volume. Don't let that throw you off. Water has a density of 1 gram per mil, so they're interchangeable. That's your mass. There's a temperature, but it's not a temperature change. It looks like your delta T is 75 degrees Celsius. And we are solving for Q, and the fact that it's water means we have C as well. It is liquid water. And there's its resistance to temperature change. So plug them all in, and you should get 74,371 joules. This is an introduction to measuring energy.